Hello, everyone. Welcome. Thank you for joining us. I'm Julia Upton, IEEE Maine Section Chair and IEEE Maine Section Joint Computer Society and Communication Society Chapter Chair. Again, welcome, everyone. Big thank you to the sections co-hosting this event, New Hampshire section, New York section, and Boston section. Thanks to IEEE Region 1, IEEE USA, and our friends who are broadcasting this event in Asia, in China, and India. So once again, we're so glad to see everybody. And the topic for today is explainable AI, hopes and hypes in healthcare. We will first have the three presentations and then Q&A at the end. So if you have questions, please type them into the Q&A. Not chat, but Q&A. And then we'll have a lively discussion after the three presentations. Our first speaker today, and I am honored to welcome Dr. Hongfang Liu. Dr. Hongfang Liu is Professor of Biomedical Informatics at the Center for Clinical and Translational Sciences at Mayo Clinic. Dr. Liu's primary research focus is to facilitate the secondary use of clinical data for clinical and translational science research and healthcare delivery improvement using data science, artificial intelligence, and informatics approaches. Her research has been extensively funded by the National Science Foundation and the National Institute of Health since 2003. She's a fellow of the American College of Medical Informatics and deputy editor of Health Data Science Journal. Welcome, Dr. Liu. The stage is yours.
Great. So am I unmute now?
Yep.
Great.
I can hear you. Mm-hmm.
So thank you. Thank you for the invitation. So here I'm going to cover something related to explainable AI with the lead component of this. On the top, you will see we're going to emphasize something which is aligned with the healthcare side. I'm from Mayo Clinic, so we have this momentum of healthcare side. The emphasis is focused on three pieces. One is hope, trust, and science. So you will, after the end of the presentation, you will see why it's so important to have explainable AI in the healthcare systems. When you bring health AI. So the outline of the talk, first, digital transformation of healthcare creates a lot of opportunities, but there's challenge faced in healthcare AI. How do we ensure we take a human-centric, responsible AI approach, and where the principle we promoting in the healthcare AI domain on the topic, which is right, fair principle. Direct go to every of you know that when digital transformation has been very active in the whole field, the whole society, when you come to healthcare domain, this is the slide to show that we actually summarize the healthcare itself on the data component into 6 characters. One is the genetic side of the information. Secondly, is all the information we connect through our digital activity. We think we have huge data, big data, and such a big data will enable us to reboot healthcare, reboot medicine. And so we are going from disease care to actually healthcare, where we start from prevention and going down to the prediction management, as well as, diagnosis. All those different pieces we can leverage data to handle and leverage digital technology to help that delivery, where AI, artificial intelligence, play a significant role. And meanwhile, such a big data connection, why we think that there's rebooting opportunities. We all know there are different for health and well-being factors. For individuals, the social and environmental factors pay 20%, individual behavior is 40% of the contributing factors, genetics about 30%. But when you come to the healthcare itself, it's only 10%. Most of the healthcare, the data available in healthcare is very small. A major of the data pieces are actually around, which are not captured in the healthcare itself, such as electronic health records. And the majority of the healthcare organization currently looking for, the whole piece of this rebooting from the digital transformation, where you see most of the academic and medical center will have three major pieces. One is precision medicine. How do we leverage the genetics and all the precision information gathering to help us to deliver individualized care, precision care. Secondly, it's about a learning healthcare system. So where can we, leverage the data to help us improve our care? The last one is digital transformation, where how can we leverage all those data capture modalities, capture information which is not traditionally captured in healthcare delivery, healthcare practice, and leverages that to improve the care. And of course, all those require a whole look from the clinical translational science space, where we start from basic research until we go to the population social policy side of the research. So this is the things we have been keep emphasize. There are three major kind of skill sets and disciplines we needed to work together in order to achieve that goal, where the discovery component in the rebooting and digital transformation in the big data side, we need to leverage a lot of data science innovations and methods to facilitating that. And in the translation pieces, which is basically how to bridge the discovery to something which can be implemented in practice and to benefit individual patients. The last one, of course, come to the application. When we look at the healthcare AI, we mainly look at the healthcare AI as an application where we leverage what we learn, what we discover through data science, through machine learning, through informatics tooling, and to deliver that to the point of care. And we, in the discovery side, we actually see major efforts across through the social media, through the news. You guys probably already know that the AI technology has already facilitating a lot of things which historically cannot be done before. The Google DeepMind, for example, release structure. This is about AlphaFold. And then you see Google also have this large language models, which they try to use those technology to bring to application. In the National Institute of Health side, and many of you probably hear, there's a initiative called Bridge to AI, which is focusing on getting more ethically connected data to advance healthcare AI and AI for biomedicine. So in each individual kind of healthcare institution, academic or medical center, this is what's being put as there are 10 emerging trends. Almost those emerging trends in health IT, you can see depends on digital transformation, things enabled through digital transformation, and the things enabled through data science and informatics. And all those things means that when we talk about healthcare AI, what's happening is the happening into real world. It's happening to individual patients right now. And it's no longer an ivory tower practice, but more as the things in action. However, we talk about a huge potential there, but there's also challenge facing healthcare AI. I will walk you through that. There are major challenge. One major challenge is data ownership. Who owns the data? And secondly, the data, besides the data ownership, there are a lot of things we as a practitioner of healthcare AI, we know, data is not the only thing, because in real world data, there's so much noise, such a bad quality, because they are real world data. So there are many things around it. So it require, truly take a scientific approach to look at the use of the data and how to ethically use the data, all those pieces. So data ownership is one big challenge we face. Secondly, another challenge faces we call digital divide. This is especially important in health disparity domain. We know we have social structural bias, social determinant of health, all those pieces play significant role in healthcare. And when we use data, but those from social disadvantaged population may not have data available for us to train models. And so therefore the application and the solution we propose and we develop, we will probably increase the digital health disparity and due to the digital divide we have in the domain. And most of you also hear, this is an article done in the annual review of biomedical data science, which talk about ethics, machine learning, and healthcare. So when the actual application has a potential impact to individual patients, to individual person, the things we actually need to look very carefully across the whole life cycle of AI generation or product generation. So basically, we have the data. Does not mean when we work on a problem, we choose the problem which may have a potential to harm some group. So the first one is problem selection, right? So the disparities in funding and the problem selection priorities, it is ethical violation of principles of justice. Data connection, this come to digital divide component too. How do we, when you use a convenient sample, that can exacerbate existing disparities. On the outcome definition and algorithm development and the post-deployment considers so many things on the ethical side. When it comes to healthcare AI, we needed to consider. And there are many potential, pieces. There are things visible we as a data scientist, AI practitioner can see. However, there are many hidden pipeline challenges we don't know. And I bring this topic. This is basically means that it is so crucial to take explainable AI approach and team science approach so that those hidden pipeline challenges faced here can be mitigated. And this is show you the example of a lot of things when you use convenient samples and the historical bias will be translated. For example, this is a specific example showing that when you have racial bias in the algorithm, when you use that to manage the health of a population, for a given risk factor, Black patients are considerably sicker than white patients, as evidenced by signs of uncontrolled illness. And if you look at this is actually related to, first, there's a social bias there. Secondly, they don't have enough data there either for them. Secondly, this is another example showing in the JAMA internal medicine, which shows that you have a sepsis predictor model, but when you use that to healthcare systems, you see a a huge performance degrading in that area. And this is another one showing you geographically for almost all the deep learning algorithm people were working on, what are the regions were represented. You will see dramatically for the East Coast, the West Coast, they are well represented. So you will have a lot of patients cohorts and with algorithms, you know, may benefit them, but you see all the other regions, there are very few studies which are used to train machine learning algorithms in those deep learning algorithms. And this is another example to show, you know, when you use electronic health records, the data capture for those underrepresented population, that when they have low social status, those with psychological issues and immigrants, they tend to have a huge data fragmentation, data representation issue, and of course the underlying machine learning algorithm will not perform well for them. So all those are pieces. So now come to, those are the issues of the data side, the discovery side. But when you come to say, okay, let's just trust that this, if we have this as a black box solution, what is going to happen? It's basically almost all those real world data, embedded structure bias. The black box solution definitely not be able to give the end user trust to handle that. And we know that big data-based AI product can have significant societal impacts, and ethics become so crucial. So from the human centricity point of view, black box is not acceptable, and we need explainable AI to help that. And at the same time, I want to bring people's attention. We did a lot of studies. So what we found out is that sometimes what the AI model was doing, some of those just replicating what the expert has been applied. This is showing you an example of two Bayesian network. One is the weight of the networks was derived from data. The other is showing from expert. And this diagram just showing you that when you use expert Bayesian network, when you use mind Bayesian network, you have the same performance. So it is just, you know, how do I say, the advantage of expert is explainability. And however, if you use through deep learning there, that can be a little bit lack of explainability. So go back to the what we were thinking, the future of healthcare AI. This is the kind of guiding principle published by World Health Organization, talk about when you use the health for AI for health. So first is, there are 6 principles we need to follow. One is protecting human autonomy, basically means that the privacy needs to be paid special attention here. Secondly, promoting human well-being and the safety and the public interest. Ensure transparency, explainability, and intelligibility, and fostering responsibility, accountability, and ensuring inclusiveness and equality, and promoting AI that is responsible and sustainable. I want to emphasize this is no longer just research when you talk about healthcare AI, because any of the products, any of the models you develop has the potential to be translated to a product where will be applied to individual patients. And that's the reason it's so crucial. Go back to the heading we talk about. This is the PBS piece about Mayo Clinic documentary. I want to leverage the 3 keywords here: faith, hope, and science. When we look at the healthcare, what is distinguished from other things, that healthcare is not just the science. They do bring hope and also faith. Those 2 are social, you know, those type of humanity characteristics. This we need to pay attention. So translate to the things that we want to do for healthcare AI, we needed to build a trust, which indicated we need a people-centric approach. We need to bring value, bring hope to the healthcare domain. And that means we need to add value to the healthcare. Lastly, we needed to bring science to the picture, which is evidence-based delivery. This is for this group of audience, we don't need to emphasize too much, but in the piece of artificial intelligence side, we many more as we want to take advantage of both when we try to think about healthcare AI and building the human-machine collaboration and the trust. And when you think about decision for real-world AI, those are the things that we want to show is that those things, whenever we think about solving AI problems and do an AI product application in healthcare, sometimes, we also need to think about, the potential of deployment and implementation, right? So you ensure behave as it should be, provide evidence of the decision, reproducibility, and the security. So don't want to emphasize more, but the transparency, explainability is such a big thing when you bring AI to healthcare. This is the last slides I want to just to summarize is that for real world AI, especially in the healthcare domain, we need to ensure this right fair principle, which is the model itself need to be, the process or data itself need to be need to be reproducible, implementable, transparent, and explainable. And the artifacts and anything we work on it need to take the the data principle, which is the data artifacts associated with the AI model need to be findable, accessible, interpretable, and reusable. Mostly, we needed to truly take the approach of people-centric, evidence-based, and value-added. When talk about healthcare AI, it's no longer just a research practice anymore. And I think this is the last slide. Do I do QA now, or we will do later?
We will wait until after the
Okay.
last speaker.
Okay, great. Thank you.
Thank you so much, Dr. Liu, for this excellent presentation. I see questions already coming in Q&A. Keep them coming. We will move on to our next speaker today, and that is Dr. Ahmad Tafti. Dr. Tafti is an assistant professor of computer science at the University of Southern Maine, where he is leading the University of Southern Maine HEX AI Research Laboratory. Dr. Tafti received his PhD in computer science with an emphasis on artificial intelligence and 3D computer vision. He is passionate about AI and its applications in healthcare. Dr. Tafti is the 2021 SIM Imaging Informatics Innovator Awardee, Mayo Clinic Transformed the Practice Awardee, and NVIDIA GPU Awardee, and the GE Healthcare Honorable Mention Awardee. To date, he has authored 45 plus peer-reviewed publications. Dr. Tafti has organized numerous workshops and tutorials on intelligent health systems and has served on the program committee of 15 plus conferences, symposiums, and journals in AI and digital health sciences. Well, it's my pleasure to present Dr. Tafti. And Dr. Tafti, the stage is yours.
Thank you. So you hear me well?
Yes.
Yeah, okay. So first and foremost, thank you for having me. And it's my absolute pleasure to be with you today. So today I'm going to talk about making AI models interpretable and also explainable for medical image analysis. So I would like to first talk about the outline of the talk. So I will start with recent advances in AI-powered medical image analysis. And I will continue my talk with two main messages we are seeing in AI-powered medical image analysis and also explainable AI models in computer vision, which is a sub-branch of artificial intelligence. And I will finish my presentation with demonstrating how we can make AI models interpretable and explainable for medical image analysis. So first of all, I would like to have a quick review on AI-powered medical image analysis, like recent advances as we can see in the literature. So recently, there is a publication actually entitled Advances in Deep Learning-Based Medical Image Analysis, published in Health Data Science. So the main message in that work is actually in overall, and according to the best available evidence, we can say that deep learning models or deep learning computational vision models perform well in medical image analysis. So if we want to get back to the definition, and if we want to have a little bit more about deep learning strategy and also deep learning computer vision, so we can summarize that computational vision, and in particular, deep learning computer vision has already demonstrated successful applications in many medical image analysis discipline, including, for example, image registration, image classification, image segmentation, and object localization. So recently, there has been another study led by Harvard scientists, and the work entitled Comparing the Performance of Deep Convolutional Neural Network with Orthopedic Surgeons. So, and the main message in this work is that, so the CNN, which stands for Convolutional Neural Network, achieved the same, as you can see, or higher performance than at least one of the surgeons in identifying 8 of 9 total hip replacement implant designed and underperformed all of the surgeons in identifying one total hip replacement implant design. So the other study I would like to highlight that it's explainable deep learning model in medical image analysis published recently in MDPI journal. And the main message we can see here is that deep learning methods have been very effective for a variety of medical diagnosis, medical imaging tasks, and they have outperformed human experts on some of those kind of applications. But the issue is that black box nature of the algorithms have restricted their clinical use. So within those studies and another studies we can see in the literature, so we can grab 2 main messages. So the first main message is that, so the story is and, story is not all. What I mean is that, so we are going to have deep learning, computational vision, to have AI-powered medical image analysis, plus our surgeons, plus our radiologists, plus our physicians. We are not going with the use of AI-powered models. The main message is this: we are not going to replace surgeons. We are not going to replace radiologists, even naive radiologists. So the main message here is that we have deep learning computational vision and surgeons. So we keep human in the loop. The second message here is that while scientific progress in AI-powered medical image analysis, in deep learning computational vision and pattern recognition has actually led to advanced modeling strategies with almost like human-like performance, but they are limited. They are still limited in their explainability and interpretability. So we can summarize this in 2 different, kind of pipeline. So the first one, as Dr. Hongfang truly mentioned, it's what is the rationale behind AI-powered decision-making. We call it explainability. So, and the second one is that what is the meaning of this AI-powered decision-making? We call it interpretability. So before I go to the next couple of slides, I would like to spend some time to show some sort of differences and differentiate we have between rule-based AI strategies and learning-based strategies, learning-based AI strategies, specifically in the area of computer vision. So imagine, I would like to start with this scenario. So simple, straightforward scenario. Imagine we want to make an AI component like an AI software component, AI hardware components that can help visually impaired people to distinguish steps from doors. So we want to provide AI components to help visually impaired people. So to distinguish two objects from each other. So the first thing we as human is going to do is actually to define singularities, right? So we need to define singularities. So the singularities we are seeing in these two images, if we look at this step, we can see a list of, from our human vision, we can see a list of horizontal line in the steps, right? While we can see a list of vertical lines indoors, right? So the singularity we can define is based on horizontal line or vertical lines we can see in those two different objects. So in AI, in artificial intelligence community, we can account for rule-based algorithms. We can account for learning-based algorithms. So if we are going to account for rule-based algorithms, so the mechanism could be something like this. So we can capture an image. So as you see here, right? So we can capture an image. Then we can turn the image from a red, green, blue kind of three channels into a grayscale channel. Then we crop the image. Then we do some sort of contrast enhancement. And then we do edge detection with the use of Sobel algorithm, for example, right? So we can then turn the image into Fourier transform and find the, like the maximum intensity we can see in the image. And we can simply define a threshold, saying that if this intensity, if the summation of the intensity is bigger than this specific threshold, then we can say this is a stair. Otherwise, it's not a stair. So if we want to account for this kind of implementation with this kind of idea, then we will get stuck in these images. So in this image, you can see we still have a list of horizontal lines, but they are not a step. But our algorithm, our rule-based algorithm with this definition, with this pipeline we see, right? So it detects these kind of objects as a stair, as a step, and it's not a step. So it will do same with this object, but it's not a step, right? So instead of utilizing rule-based mechanisms, we can account for deep or machine learning algorithms in which we need to train computers at recognizing doors from steps by showing them large amount of pair including object type and also picture, including, for example, object type is door, and the image, for example, image 1 JPEG, image 1 PNG, whatever. So what I mean is that in the simplest way, we can come up with two folders, but two directories, including steps and doors, in which indoors we will have a list of variety of doors from different angles, with different materials, with different illumination, and steps at the same. And you can see somehow advantages of learning-based strategies versus rule-based strategies. In here, we can provide machine with a more diverse model from different perspectives. So, and the machine will learn from features, from data representation to distinguish steps from doors. So get back to explainability. So here in this slide, you can see two axes here. So one, I call it model explainability, and the other one, we call it model accuracy. So in terms of explainability, if we want to account for rule-based model, so we can see that rule-based model, they are generally, explainable, easy to explainable, and comfortable to explainable. But they have some sort of issues, as you saw in the last slide, in terms of model accuracy. So some people, we can call it model performance, but in performance, we are focusing on accuracy. So if we go further, a little bit higher to utilize statistical model or even machine learning models, so we will increase model accuracy, but at the current stage, we are losing some sort of explainability of our models. And if we go in advanced techniques like deep learning strategies, deep learning computational vision strategies, including, for example, deep convolutional neural networks, then we will have, very nice accuracy, very nice performance, include similar, like, very nice precision, recall, those kind of things. But we will have some sort of issues in terms of explainability. So deep learning models, somehow they need to, they need to discuss. So we need to explain what's going on under the hood for deep learning methods. So as part of computer vision model explainability, I am focusing on computer vision model in terms of explainability. We as AI scientists, we actually need to come up with 3 different criteria. One is model interpretability. With model interpretability, we want to make sure that AI-powered decision-making is natural and we can't see any bias. So we are going to develop unbiased in our prediction model, in our predictive models. So the second thing we want to see, and we need to cope with that, is model transparency, to actually make sure that we are differentiating false casualty from true casualty. So the third one, or the last one, is actually trust. It's very, very key participant. So enable real world decision makers, enable our physicians, enable our nurses, our practitioners, our surgeons to trust AI-powered models. So AI-powered models explainability actually aims to achieve several kind of things. So first of all, trust. So convey confidence in the model to our end users. So second one, we can say correlations. So in correlations, we are going to capture correct association correlation among various features we have, and see whether this is meaningful correlation or it's not meaningful correlation. So, and the third one is privacy, is preserve privacy, identity, as Dr. Hongfang truly mentioned. So in the couple of last slides in terms of, World Health Organization. So the criteria we saw that it was also about identity. So we want to preserve privacy and do some sort of identity management. So this is one of the things that explainable AI will help us to get there. So fairness is another thing which is really important. We want to be fair in our AI model, and we want to, to actually take care of ethically compliant. So we should be imagine only for data perspective, as an example, for data perspective, we all know that, so data has 2 sides. One side of the data is quantity of the data. The other side of the data is quality of the data. In both sides, we need actually to be really careful in terms of different ages we have in our data, again, quality and quantity, in terms of different, like ethnicity, different race, amount of the data in different race, quality of the data in different race, in different ethnicity, in location, so age, whatever. So reliability is another thing. So we want to be confident in the AI-powered models. So now I want to show how we can achieve these like AI explainability in medical image analysis. So first of all, in this slide, you can see we can categorize, like in a very big umbrella, we can classify AI explainability models, or the way we can provide some sort of explainable AI. We can classify explainability into 3 different categories. One, we call it example-based explainability. The other one, we can call it textual-based explainability. And the third one, we can call it visual-based explainability. So in terms of those strategies, those mechanisms, I would like to finish my presentation with 2 case studies. So the first case study I want to show you in terms of medical image analysis and also explainability in those analyses, in those AI-powered analysis, is this. So we all know that in a daily basis, our surgeons, our practitioners, they are facing with this sort of X-ray images. What I mean is that X-ray machines normally generate this sort of image, but end of the day, our practitioners, our surgeons, they are actually really interested in the region of interest here. They want to find any complications, you know, any, let's say, for example, infection, bone lucency, bone loosening, whatever, you know, kind of complications in this slide. So the region of interest, we can say this part of the image. So we can generally say, you know, they are not interested in this part majority of the time, and they are not interested in this part. But the problem is that our X-ray machines generate this kind of image. So what I'm trying to say is that, so end of the day, we want to make an AI model that can do two different things. One is to localize region of interest. We call it localization, right? So localize region of interest, and also classify region of interest into different categories, saying that this region of interest is TKA from lateral view. For example, TKA stands for total knee arthroplasty. So in the second example, you can see this is the original image generated by X-ray machine. So our surgeons, they are interested in this part of the image, like the region of interest here, sorry, I mean here, region of interest also, you know, here. So what I mean is that end of the day, we want to have our AI model to actually provide bounding box here, and also classify these as this is knee from AP view, this is total knee arthroplasty from AP view, not from lateral view. So in terms of explainability, so we started the project like this. So we had, and we have our physicians, you can see expertise in the loop. You can see domain expert in the loop. So we did account for our, for domain experts, physicians to be in the loop. They actually provided us annotation guideline. So what I mean by annotation guideline is something like this. So, okay, so how we can grab knee AP manually, not with the use of AI. How we can grab knee lateral manually with within these plain radiographs, right? So, and then with the annotation guideline, our physician developed, right? So we actually had 3, 4, 5 different annotators to try to annotate data manually. Then we want to feed those kind of manually annotated data into deep learning computational vision to come up with some sort of automatic, objective kind of prediction. So, and we actually ended up with intersection over union over, 90%. Intersection over union is going to show us how two segments, how two actually region of interest, they are similar to each other. They are matched to each other, right? So an F1 score in terms of classification. Let's say, for example, the first surgeon, the first physician actually annotated the data into TKA view, and the second one also TKA view, and the third one is also TKA view. So you can see high rate in terms of localization. You can also see high rate in terms of classification. So, and it was, that work was actually based on example-based explainability. What I mean is that we provided our surgeons, end of the day, this is the result we provided to our surgeons, and this work published with this name. So, and the clinical significance of this work was actually about pre-post operative knee surgery. So, and we provided our surgeons, our physicians with a list of examples. That's the way how a machine can do the work. In terms of, TKA AP view, different examples I'm saying. Knee AP view, TKA AP view, TKA lateral view, you can see different examples from different perspectives. Lateral view, AP view, you can see different knee models in terms of this is a plain knee or this is knee with, TKA, with total knee arthroplasty. So, and as always, we had our physicians in the loop. As I said in the beginning of my presentation, the story is and, not or. AI-powered model and physicians. So have them together and they will be working together to come up with this kind of nice, very accurate kind of result. So the second one, I would like to finish my presentation with this slide. So it's like we utilize visual-based kind of explainability here. And this work has been published with this, kind of title here. And the clinical significance of this work was actually about knee revision surgery. So, and here, as you see, so in terms of visual-based explainability, we were able to provide some sort of heat map within different knee TKA implants. And the work was actually tied to identifying 4 different TKA brands within plain radiographs. And in these images, you can see that AI models is telling us, so I as AI model is looking at this part mainly, is looking at this part mainly, and looking at this part mainly to distinguish brand of tritolone from brand of Sigma, for example, right? So, and if we turn the perspective from AP view to lateral view, then we can see that AI model is telling to our physicians that I as AI model mainly looking at this part, and perhaps at this part to distinguish triathlon from Sigma. So with that, I would like to stop my presentation and again highlight that even in this work, in every single work we are doing, we are keep human domain expertise, domain experts, it all in the loop to make it happen. So thank you all, and I will finish my presentation here, and I will be happy to take any question you may have. Thanks. You are muted, I guess, Julie. You are muted. Dr. Upton, you are muted, I guess. You are on mute.
Oh, there we are. Thank you. Thank you. Yeah, I was wrapped up in your presentation. I had to unmute myself. They're really fascinating. Thank you so much. Our last speaker today is Dr. Wang. He's Vice Chair of Research and Assistant Professor with a primary appointment in the Department of Health Information Management, School of Health and Rehabilitation Sciences, and secondary appointments in the Intelligent Systems Program, School of Computing and Information, and the Department of Biomedical Informatics, School of Medicine at the University of Pittsburgh. His research interests focus on artificial intelligence, natural language processing, NLP, and machine learning methodologies and applications in healthcare. His research goal is to leverage different dimensions of data and data-driven computational approaches to meet the needs of clinicians, researchers, patients, and customers. He joined Pitt in June 2021 from the Mayo Clinic, where he still holds an adjunct assistant professor position. Well, welcome, Dr. Wang. Take it away.
Thank you for the introduction, and I will keep it really quick so that we have some time for Q&A. So today I'm going to talk about the clinical NLP and how to apply explainable AI in clinical domain. I'll skip this slide. So this is basically what is NLP, and I assume everyone knows what is NLP. So, and we all know that the electronic health record is a longitudinal electronic record of patient health information generated by their clinical encounters in many different care delivery settings. So following the High-Tech Act law in 2009, many healthcare institutions have adopted EHR systems, and the size of the EHR system increased dramatically in the past decades. So this figure shows different kinds of data types available in the EHR data. So basically, EHR data has here I didn't include the image data. So here is mostly about the structured EHR data and unstructured EHR data. So structured EHR data, for example, the demographics and diagnosis code, procedure code, and those kind of, they are well structured and stored in the relational database. But there are a lot of other data, like unstructured data, like those clinical narratives written by clinicians and nurses, like clinical notes, radiology reports, pathology reports, those type of data types. And of course, medical images and signals data like EEG, ECG, they are also available as part of the EHR data, but not included here. And as the previous two speakers mentioned, that the reality of the EHR data is that 80% of the data, useful information, is embedded in an unstructured format. And only 20% of useful information is a structured format. And within those 20% of structured data, like demographics, diagnosis, it's not accurate for many diseases. So because those diagnoses, for example, the diagnosis code, the purpose is to get the medical bills reimbursed by insurance. So those medical bills diagnosis code is not accurate, and a lot of the accurate information is actually documented in the clinical notes. So that's why the NLP, the natural language processing AI technique, is usually used to handle the unstructured data and extract the useful information from the unstructured data. So here are some useful applications of clinical NLP. So for example, the question answering in NLP, a lot of, if we go to those websites like COVID-19 website from WHO or CDC, they are actually using those question answering techniques as an interface to interact with users. So when the users ask some COVID-19 related question, those chatbot will return some answers. So on the back end, those chatbot are using question answering techniques. NLP is also covers information extraction. So for example, in the clinical domain, we actually use a lot of information extraction. And when some when some researchers in the clinical domain talk about NLP, they are actually talking about information extraction. Means they want to extract some information from the clinical notes. So in this case, for example, a lot of risk factors are stored in the clinical notes. In this case, this is a family history. So family history is a risk factor for many diseases like mental health disorders and cancer, a lot of cancers. And those family information, they are stored in clinical notes. So if we want to extract those family history information, like family members, their healthcare, their health conditions, their living status, as well as the associated age information, we need to use information extraction technique. So here we usually need two subtexts in information extraction. One is named entity recognition. So we have to recognize those named entity from the clinical text. And then we apply the relation extraction to link those named entity and build a knowledge graph so that we know the whole picture of the family history of the patient. So NLP is also also about the information retrieval. So we're using that through those search engines and also like a PubMed when we want to search those literature. And the NLP is also about a sentiment analysis. And the sentiment analysis is used to, sentiment analysis is widely used in online retailers like Amazon, because whenever the customer buys some products, they check the reviews and then make decision whether to purchase that product or not. And also sentiment analysis is used in a healthcare domain to improve the patient experience, whether they are satisfied by the hospital service or not satisfied. So those are applications. And we all know that when we build those NLP or AI models, we all know that the garbage in, garbage out principle in data science and AI. So the poor quality of the input data will always result in poor quality of output or poor quality AI models. So this is especially the case with AI in healthcare, as EHR data is very heterogeneous and EHR data is real world data. They generated from the real world clinical practice. And machine learning algorithms are very dependent on the accurate, clean, and well-labeled training data to learn from so that they can produce accurate results. So if the EHR data is not accurate, not clean, and very messy, it is no surprise you will get a garbage result from the AI model. So it is for this reason that a vast majority of the time spent during AI projects in healthcare are the data collection, data cleaning, data preparation, and gold standard annotation. Like Dr. Tafti just mentioned, the annotation for the explainable, building explainable AI. And then speaking of the gold standard annotation, is a very challenging task in the clinical domain. So one physician may not agree with another when making a decision or a treatment decision, right? So this inconsistency actually exists everywhere in the EHR data. So this is an incomplete list of domains in EHR data quality. So we have to check the data quality of the EHR data before we build the AI model. So the EHR data quality includes like data accuracy. So data accuracy may define as the overall the truthfulness of the EHR data. So the degree to which the value in the EHR data is a true representation of the real world value. So there are many causes of data inaccuracy. For example, in a letter published in the British Medical Journal, researchers found that more than 1,600 adults aged 30 and above were coded in the EHR as using outpatient pediatric psychiatric services. So the authors conclude that the findings reflect that the coding errors are very common in the electronic health record. And data completeness is the degree and the nature of the missing values with EHR-based database and a secondary database. So for example, clinical clinicians, they forget to document a patient's BMI in the EHR. And the male patients are less likely to answer a screening question about anxiety, and patients may be relocated to another place. So the data of that patient is missing. So data consistency is also another problem in the EHR data quality. So it refers to the consistency of the data at the desired degree of detail for the study purpose within and across database and data sets. So for example, a study of survival in patients with pancreatic cancer, the people found that inconsistent documentation of chemotherapy across several similar data sources, as well as inconsistent use of ICD code for the diagnosis of diabetes with the same data source. So those inconsistencies actually significantly impact the reliability of the data and to use the data to develop the AI models. So the other two domains of data quality, like data credibility and the data timeliness, is also important, but I'll skip this due to the time limit. And the free text EHR is also very complicated to analyze in the clinical NLP. So this is an example from the real world EHR data about how the patient family history information is documented in clinical notes. So as you can see, there are many ways to document family history. So it could be either semi-structured or totally free text here, or maybe combined, semi-structured and some free text. So there's no standard to follow, and it really depends on the healthcare provider, how they documented those family history in the clinical notes. And it brings a lot of challenges for the secondary use of such data in building AI models. And another problem is like a portability. So if you build an AI model in one institution, does your AI model or NLP model can be portable to another institution? Because different institutions adopt different EHR system. And even the same institution may adopt a different EHR system. So at our local hospital, the UPMC, they actually adopted several EHR systems across different settings. So those EHR systems, they have different data standards, and it's very hard to serialize the data and use the data and develop a constant, AI model that could perform consistently across different EHR systems. And this is an article published recently about the 6 Ds of creating AI-enabled system. So those are the critical components the author talk about how to build AI-enabled system and ethical AI system. So it talk about decomposition, domain expertise. I can briefly talk about like decomposition. So AI technique is also pursued without significant thought on the underlying problem that could benefit from AI. So decomposition gave the stakeholders and the designers idea is the redefining the narratives of the technique concept, understanding how the technology, how the AI technology will be used, and conduct some technical evaluation of the models and comparative value assessment, and then integrate the input from different innovation actors like stakeholders in the healthcare, so to see whether this AI model is really needed in this situation. So domain expertise is in the healthcare domain, we need physicians and we need the input from those expertise, in addition to the experts who can develop the AI model. And the data also, we talk about the data complexity in the EHR system. And in the EHR system, a lot of the data is generated by the ETL process. And whether those data is well engineered to build the AI model, so that's something we also need to consider. And the design, diagnosis, and deployment, those are also important components to build ethical AIs. So I'm going to skip this. If you are interested, you can read about this article. And there are also many similarities between the warfighters and our healthcare providers. So here I want to go through the 5 AI ethical principles based on the recommendation from the Department of Defense Innovation Board. So AI, when we build AI models, the AI model should be responsible, and our human beings should be responsible when we build AI model. So the human personnel will need to exercise appropriate levels of judgment and care when we build this AI model, deploy the AI model, and use the AI model. So AI should also be equitable. So we need to take the deliberate steps to minimize the unintended bias in the AI capabilities. An AI model could also need to be traceable, because when the AI capability is deployed or developed, so we need to understand the technology, develop some process and operational methods that are applicable to AI capabilities. For example, we need to develop some transparent, auditable methodologies to monitor those AI models, data sources, and the design procedures and documentations how we develop those AI models. And the AI model also need to be reliable. So the AI capability will need to have explicit, well-defined uses, and the safety, security, effectiveness of such capability need to be tested, need to be assured before using those AI models in the real application. And through the whole entire life cycle of those AI models should be tested and evaluated. And the AI model also need to be governable. So that means we will design and engineer the AI capabilities to fulfill their intended functions when we put those AI model in the real world application, for example, the clinical practice. So those are the principles that has been recommended by Department of Defense for the warfighters when they use those AI models. And I think those principles also apply in the clinical domain, because it's very critical when we treat the patients with those, using the AI models following those principles. Okay, I think we are on top of 1 hour, and I hope we have some time to answer questions.
Thank you, Dr. Wang. And yes, we're over technically out of time, but we're going to hang out for a few more minutes. Thank you very much for the participants for answering questions in the Q&A. Those are 7 questions that were answered. We just have a few open ones. For developing and validating models to have physician in the loop, as physicians become accustomed to being assisted by AI models, their own performance or interpretations may change. The current state of trust, skepticism of AI results may be critical to the performance of an AI-assisted physician. Does this shift in physician behavior then negate the previous validation qualification of the AI-assisted decision-making process? So any of the panelists would like to jump in to address this?
I think I can comment. This is a significant question we are facing, is that how do we continue monitoring the system to ensure the data distribution will stay similar in order to, for those models to be applicable. And the second thing, actually, we are significantly concerning about this because most of the AI models was trained using real world data. And the real world data we consider is the knowledge plus experience together. And different providers have different experience in this situation. We are concerning about the future where the human may lose the ability to gain such an experience to be able to generate new knowledge in the space, a new discovery. So all the question you ask is really makes sense. Currently, is that we say AI has a huge potential, but how are we actually implemented into a human computer reinforced kind of learning ecosystem that still need to be think and design and frame.
Thank you. So yes, there are questions in the chat about availability of the presentations. Yes, the recording will be available, and we can also make available to everyone who participated in the webinar the slides of the presentations, correct? Yes, excellent. Excellent. So thank you everybody so very much. In particular, the University of Maine Office of Associate Vice President for Research for hosting the webinar. Fascinating talks. Thank you everyone again for joining us. Have a great rest of the day.
Thank you.